Imagine a place where the boundary between the ground and the sky is blurred by machines that push beyond the limits of conventional physics. China is promoting T-Flight, a vacuum tube magnetic levitation transportation system designed to reach speeds of approximately 620 miles per hour, faster than many commercial transportation networks in operation today. After real-world tests reportedly reached roughly 387 miles per hour in early 2024, Beijing appears determined to shape the future of ground transportation by connecting major metropolitan regions in a matter of minutes rather than hours. This rise has created growing pressure across the West. Is the United States being left behind in the transportation race of the 21st century? The skepticism is understandable. High-speed rail projects across America have often faced delays, cost overruns, or years of planning before construction. Yet behind that apparent silence, a very different strategy is taking shape inside factories, laboratories, and aerospace facilities across the United States. Rather than competing directly on increasingly expensive rail networks, America is attempting something more ambitious: a leap toward the 22nd century through supersonic and hypersonic transportation, where speed is no longer constrained by wheels, tracks, or the friction of Earth's surface. The foundation of that confidence is economic strength and access to capital. The United States is not relying solely on federal infrastructure spending through the Infrastructure Investment and Jobs Act. It also draws on enormous pools of private investment. While China's rail sector carries hundreds of billions of dollars in debt to maintain its vast high-speed network, American aerospace and logistics companies operate under intense pressure to generate profit, efficiency, and long-term shareholder value. The private aviation and logistics sector alone contributes nearly 9% of U.S. gross domestic product, creating a technology ecosystem where every investment dollar is expected to produce measurable returns. This is not merely a competition between machines. It is a competition over capital efficiency and long-term strategic vision. American planners increasingly believe that success in the age of advanced reality will require transportation systems that are more flexible, faster, and less dependent on costly fixed infrastructure. The first major answer is Boom Supersonic Overture. This is not a science fiction concept. It is a real aircraft program supported by the company's Super Factory in North Carolina. Overture is designed to cruise at approximately Mach 1.7, or more than 1,100 miles per hour. That is nearly twice the target speed of China's experimental T-Flight system. The key innovation is the Symphony engine, a propulsion system designed without afterburners in order to reduce noise and improve compatibility with sustainable aviation fuel. Another breakthrough is something called boomless cruise. This technology aims to refract shock waves upward, allowing the aircraft to exceed the speed of sound over land while minimizing the disruptive sonic boom traditionally associated with supersonic flight. The challenge is straightforward. How do you transport thousands of passengers at supersonic speeds while keeping ticket prices closer to business class travel? Overture's answer is altitude. By operating at approximately 60,000 feet above sea level, where the air is significantly thinner, the aircraft experiences far less aerodynamic drag. That reduces energy consumption and eliminates the need to push hundreds of tons of metal through a vacuum tube buried beneath the ground. While Overture is attempting to redefine civilian aviation, the pressure created by China's rail network remains impossible to ignore. By 2026, China had built more than 31,000 miles of high-speed rail, accounting for roughly 70% of the world's total high-speed rail network. This massive system connects cities across the country and extends its influence through the Belt and Road Initiative, reducing freight transit times to Europe to roughly 12 to 18 days. The extensive network of CR400 trains operating at approximately 217 miles per hour has created a significant advantage in scale. Yet this achievement raises an important question. Is investing hundreds of billions of dollars into a fixed transportation system really the smartest strategy in a world that is changing at an unprecedented pace? China now faces growing pressure from debt obligations and the enormous maintenance costs associated with rail lines that serve relatively low passenger volumes. American planners have watched this closely and chosen a different path, focusing more heavily on freight efficiency than on expanding passenger rail mileage. The difference in America's logistics strategy lies in maximizing existing infrastructure while integrating emerging technologies. The United States currently operates the world's largest rail network, spanning more than 140,000 miles. But instead of prioritizing passenger transportation, America has transformed this network into one of the most efficient freight systems on Earth. A typical freight train can move 1 ton of cargo approximately 500 miles using just a single gallon of fuel. That is roughly 4 times more efficient than trucking. Private railroad operators such as Union Pacific and BNSF have invested more than $825 billion into infrastructure improvements without relying on massive direct government subsidies. The result is an intelligent logistics ecosystem. Rail handles large volume cargo. Highways provide flexibility. Air transportation delivers speed. America does not need to build tens of thousands of miles of new passenger rail to achieve economic efficiency. Instead, it focuses on reducing total logistics costs to roughly 7.5% of gross domestic product, significantly lower than China's estimated 14%. This approach helps explain how the United States maintains its economic strength, not by pursuing the largest numbers, but by maximizing efficiency, technology, and return on investment. The next breakthrough arrived on May 26, 2026, when Hermes achieved another milestone with its Quarterhorse flight program. Quarterhorse is an American hypersonic aircraft initiative that officially reached approximately Mach 1.21 during testing in New Mexico. But Quarterhorse is much more than an aircraft. It serves as a test platform for the Chimera hybrid propulsion system, an engine designed to transition smoothly from traditional turbine operation into ramjet mode. The ultimate goal is sustained flight at Mach 5, equivalent to roughly 3,800 miles per hour. At that speed, a trip from New York to London could potentially take less than 1 hour. While engineers elsewhere continue exploring the challenges of maintaining vacuum conditions inside thousands of miles of ground-based transportation tubes, the United States is pushing toward hypersonic travel through the atmosphere itself. Quarterhorse demonstrates America's ability to develop breakthrough transportation technologies with the speed of a startup while leveraging the resources of the nation's defense and aerospace ecosystem. This is the essence of advanced reality, a future where speed is no longer measured simply by miles per hour, but by the ability to project people, information, and capability anywhere in the world almost instantly. However, the hypersonic race also introduces a new set of challenges involving heat-resistant materials and autonomous control systems. At Mach 5, air friction generates temperatures high enough to melt many conventional metals. America's answer is the use of advanced composite materials combined with real-time AI navigation systems capable of managing airflow, heat distribution, and flight stability under extreme conditions. America's advantage does not lie solely in the aircraft itself. It lies in the entire ecosystem supporting it, from highly accurate satellite navigation systems to the world's largest aviation network, with more than 19,000 airports and aviation facilities. That level of flexibility is something fixed-rail transportation systems can never fully match. A hypersonic aircraft can change course and reach almost any destination in the world within hours. A maglev train, by contrast, can only travel where its infrastructure has already been built. Looking at the bigger picture, we can see two very different visions for the future of transportation. China continues to expand and optimize rail technology, pushing speed and scale to their practical limits. The United States, meanwhile, is pursuing a different path, redefining mobility through supersonic aviation, hypersonic transportation, and next-generation aerospace platforms. The combination of America's highly efficient freight rail network and its breakthroughs in high-speed aviation is creating an advantage that no ground speed record alone can replicate. America does not necessarily seek to build the largest infrastructure projects on Earth to demonstrate its strength. Instead, it focuses on technologies capable of transforming the very nature of global commerce, logistics, and security. History repeatedly shows that in the race for speed, those who control the skies often shape the rules of the game. Ultimately, America's leadership position is not built on fear of a competitor's achievements. It is built on continuous innovation, a powerful technology ecosystem, and a long-term investment mindset. When Overture begins carrying passengers at supersonic speeds in 2029, and when the Quarterhorse program moves closer to its Mach 5 objective, the world may start thinking about distance in an entirely different way. Not in miles, not in kilometers, but in time and technology. America is pursuing this transportation revolution in its own way, faster, more flexible, and increasingly focused on real-world efficiency. Are you ready to witness a future where traveling faster than the speed of sound becomes as routine as commercial air travel is today? Because that future may not be found on the rails beneath our feet. It may be above us, where a new generation of American machines is pushing the limits of speed and redefining how the world connects.